Great. So thank you very much, everybody, for tuning in today. My name is Kelvin, and as Dario mentioned, I'm co-creator of Apex, which is an open source project I recently worked on. So Apex is an API proxy designed for teams that are just migrating from a monolith to microservices. And what Apex provides is one place for these teams to log and control all service-to-service traffic. So today, I'd like to quickly review some of the challenges that arise with microservices, which prompted this project to exist, and then go over some of the existing solutions to these challenges. And then I'll explain how we designed Apex as an alternative solution, and also then how it works and how it's implemented. So challenges with microservices. So it's no secret that despite microservices' many benefits, they do come with their own challenges. And so for this presentation, I'll just focus on two of them, and I'll be defining these two a bit more precisely in the context of Apex throughout the presentation. And so the first is diagnosing network faults, especially when when workflows span multiple services and logs are output to different places. And the second, managing fault handling logic that might be similar, but not exactly the same, but lives in client libraries that are scattered across different services. So these are the two challenges that I'll be focusing on throughout the presentation. And it's worth just quickly reminding ourselves that these challenges are primarily a consequence of microservices' reliance on the network. So in a monolith, this is of course not the case, because most subsystems in a monolith run on the same server. And so when they have to talk to each other, they do that through in-process calls, which happen in process, in memory, and are reliable and fast. Whereas with microservices, on the other hand, subsystems potentially run on different servers. And so these fast, reliable in-process calls that we had in a monolith, those are all replaced by network calls, which are prone to latency and failure. And so latency meaning that we've gone from the microseconds that these in-process calls need to typically tens or even hundreds of milliseconds for the average network hop. And failure meaning that requests can just be dropped, or responses can just be dropped, even if each service's code is bug-free. And so those limitations of the network, especially the network unreliability, cause the two challenges that I mentioned earlier, right? Diagnosing network faults. So often, how this plays out is when using microservices, we typically have workflows that span multiple services. Right, so this example workflow in the diagram involves 3 requests and 3 responses, and any of those could fail. Any one of those hops could fail in this workflow. But then usually the logs would for each service would be output to a different location, right? And so as is, diagnosing that fault could be slow, right? Because now the developer has to trace through that initial request through multiple sets of logs, which can be a bit of a laborious process. So that's the first challenge. And the second challenge, again, arising from network unreliability, is how you choose to preempt, right, unreliability with fault handling logic within your architecture. So sometimes when requests fail, the cause is actually random, right? So maybe instead of immediately sounding the alarm and trying to diagnose and fix the problem, it's better to just program your services to just retry the same request a few more times, right? Maybe that's actually sometimes the better way to handle the issue. But then defining this kind of retry logic has to be done very carefully. In this example, we've got orders trying to call shipping and retrying a few times. If orders retries too many times, too often, or too soon, right, that could all those retry attempts could overwhelm the destination service, the shipping service in this case. That could crash the shipping service altogether. And so, this kind of logic has to be defined carefully. Another consideration when defining this kind of logic is whether we want different rules for different pairs of services calling each other. So maybe for one reason or another, we have orders we want orders to always call. We want, whenever orders calls shipping, for orders to always wait for 3 seconds between every retry attempt and to retry no more than 5 times. Whereas maybe by default, for every other pair of services, we want the retries to wait 5 seconds. We want there to be 5 seconds between every retry attempt, and for there to be no more than two times, or 2 attempts. And so all of that logic has to, of course, live somewhere within your architecture. And usually the first solution for teams is HTTP client libraries that are imported into each service's code. Right? So if you've got a Ruby service, that would take the form of a Ruby gem, or if it's a Node service, then that would be a Node package, right? And of course, these libraries often handle a whole raft of other networking concerns as well, like rate limiting and authentication, caching, etc. But because these clients have to be imported into each service's code, they of course have to be written in the same language as the service itself. And in addition, in some larger teams, you might start to have service owners writing a client for every other service that needs to call it. Right? So in this example, in the diagram, we've got a shipping service writing a new client for calling it, right, for every other service. And when you've got different services in different languages calling shipping, then each of those services potentially needs a new client. So this solution relying on client libraries quickly becomes more and more difficult to manage as the number of services grows, because you've got a real proliferation in the number of clients you need just to manage all that fault handling logic and all the networking concern. And in this kind of architecture, now making any global updates to your fault handling logic becomes cumbersome, because now if you want to say, just as an example, right, rate limit all your services to 10,000 requests per minute. Now you have to go into each service and make that change in all the clients on that service, and then repeat with all your other services. Because that can be a very slow process that's difficult to coordinate. So just to quickly summarize, these are the 2 challenges that we wanted to solve with Apex. Because microservices rely so heavily on the network, we've got potential difficulties with diagnosing network faults and also managing fault handling logic that's similar often, but lives in different client libraries across multiple services. So obviously, some solutions exist, and Apex wasn't designed in a vacuum. And so I wanted to take this section to visit just 2 of the existing solutions for these challenges, the API gateway and the service mesh. So both of these are built upon Proxy service, the API gateway being a proxy server with a few extra features, whereas a service mesh has many different proxy servers working together. So the API gateway, typically API gateways are deployed in front of services, right? And one of its primary benefits is to route requests from clients to the right service. Another benefit is that it provides a stable API for your system, so that as developers, we could change the internal architecture, maybe replicate services, remove services, or upgrade services without the clients having to change how they call our API. And alongside those benefits, often the API gateway also comes built in with features for managing other networking concerns like authentication and caching, rate limiting, and the lot. So going back to our challenges, so how could an API gateway provide a solution here? So perhaps one solution is to deploy it internally between services. So now, rather than being a front proxy that mediates requests from clients, we could have it proxy service-to-service traffic instead. So if we do that, then we would now have one place in the API gateway to do all the logging that we needed and to manage fault handling logic. So the diagram shows kind of what this could look like, right? An internal API gateway, in a sense. So theoretically, that could work, but existing API gateway solutions aren't really quite optimal for this. And that's because because they're designed for client-server traffic, they come built in with many features that are specific for that use case, right? And those add unnecessary complexity if we're using an API gateway not for client-server traffic, but for service-to-service traffic. So, however, that is still a useful pattern. And in fact, it's a source of inspiration for Apex's architecture. So we will come back to this architecture later on. The second solution, the service mesh. So just in case not everybody is familiar already with service meshes, these are the two main components of a typical service mesh. Sidecar proxies, sometimes referred to as the data plane, and a config server or control plane. So sidecar proxies, so what these are, usually in a typical service mesh, every service would get its own sidecar proxy. And usually that would be deployed in the same Kubernetes pod alongside its parent service. So every service now, whenever it needs to talk to another service, they no longer communicate directly with each other. Right? Instead, they do so exclusively through their respective sidecar proxies. And this allows networking concerns like retries and routing and caching and all that to be handled by these sidecar proxies. Right? So, and the benefit is that each service's code can now focus just on its core business logic while outsourcing all the networking concerns to the respective sidecar proxies. The second component, the configuration server. So how this works is usually the config server sits outside of your actual sort of service architecture. So it doesn't sit on the path of any service-to-service traffic, right? Unlike the sidecar proxy. So you can see in the diagram, it's sort of wandering about at the top of the diagram. So it doesn't really mediate any requests or responses. So what it provides is instead a source of truth for all your configuration data related to networking concerns. So things like routing, tables, and rate limits, and retry logic. And whenever you need to update any of that configuration data, you do that in the configuration server, right? And then once you've done that, any updates you make are subsequently automatically pushed to each sidecar proxy's cached copy. And so that's how a configuration server works. So again, going back to the challenges that we wanted to solve with Apex, the service meshes are, in fact, already a very strong solution. The configuration server is that one place that we needed to define and update logic for fault handling, whereas the sidecar proxies execute that logic, right? And also, the sidecar proxies can handle all the logging for requests and responses between services. Furthermore, a service mesh is also very scalable and resilient a solution, since there's no longer a single point of failure or a single traffic bottleneck. However, the trade-offs here are increased complexity potentially, because now you're operating and deploying double the number of components, right? You've got at least one, you've got a sidecar proxy for every service plus a configuration server. And this is especially true. The complexity is especially true if with some of the first generation solutions like Istio and Linkerd, which should take some time to learn and understand. There are some better options if your services are on Kubernetes already, but if you can't easily redeploy your services with containers or Kubernetes, then you're not really left with many great options for a service mesh. So to quickly summarize these two alternatives, we've got an API gateway, which is relatively simple to deploy and operate, just because it's mainly just one component, but it's not really optimized for managing service-to-service traffic, which is what we're concerned about here. The service mesh, on the other hand, provides a more scalable and resilient solution, but it could require you to redeploy your services with containers and Kubernetes, or if not, then there's more complexity with the options you have to deploy and operate a service mesh. So when we built Apex, we decided to choose a different set of trade-offs. So we specifically chose to focus on teams that have just started migrating a monolith to microservices. So they might have just a few services, say fewer than 10, not many services. And these services are, let's say, they're not yet deployed with containers or Kubernetes, and may even be deployed on a PaaS solution like Heroku. So we'll assume that this team has already been experiencing the problems we outlined earlier, and are looking for a solution to help them manage service-to-service traffic. And in particular, they want to be able to aggregate their logs and manage traffic rules in one place. And this tool needs to be simple to deploy and simple to operate, and also ideally won't require any changes to how any of their solutions, any of their services are currently deployed. But in exchange, some sacrifices could be accepted. So fewer built-in features, lower availability, lower scalability. So those are the trade-offs we chose when building Apex. So at a high level, Apex is simply, as I mentioned at the very start, an API proxy. So when a team deploys Apex with their microservices, Apex will sit on the path of all service-to-service traffic. So you can think of this as comparable to the internal API gateway architecture that we saw earlier. Zooming into Apex a little bit more, you can see that we have several more components in addition to the proxy. So there's a logs database at the bottom. There's a configuration store. There's an admin API and also an admin UI. And I'll be explaining what each of these does in due course. And zooming in even further into the proxy, you can see that the proxy, in fact, has a number of middleware layers. So there's a layer for authentication for Apex. There's a layer for routing, a layer for retry, a layer for logging. And yeah, so this is how we decided to divide up the functionality to handle different networking concerns with middleware layers. So how does this architecture provide us with a solution to the challenges we mentioned? So we'll explore these two challenges again one by one and talk about how Apex provides a solution here. So diagnosing network faults. So once Apex has been deployed, whenever a service A calls service B, every one of those requests and responses between two services, or in fact between every pair of services, passes through the proxy, right? And because of that, the logger middleware can send a log to the logs database for every single request and response that goes through the proxy. So that functionality is very similar to log aggregation solutions, with the main difference being with Apex, you no longer need to install any log shippers, or any SDK or any agent within your service. And then to make those logs more useful for diagnosis, Apex also supports tracing. So each request and response passing through Apex gets given a correlation ID header value before being logged, so that every request and response belonging to that same cycle has the same correlation ID and can be queried together in the logs database. And that tracing can also support multi-service workflows, like in this example. As long as every service knows to propagate any tracer it receives, then all requests and responses belonging to the same multi-service workflow will get the same correlation ID header value before it's logged to the logs database. That means that diagnosing network faults becomes much easier, because now there's one logs database you need to query in order to get all the logs, all the requests and responses belonging to the same workflow. And we also provide, and the admin UI also provides developers with a convenient way to do that, right, without actually having to SSH into your logs database instance. So here's a quick demo. So it goes a little fast, but essentially what's happening is we're sending a request to another service through Postman, right? And in this case, that other service is just the CNN website. And we're doing that through Apex. So we get back a correlation ID header in the response. So you can see at some point we're copying and pasting a correlation ID header value from, so here, I think this is where we do it. So we're copying and pasting a correlation ID header value in the response in Postman, and then we are opening up the API UI and punching in that correlation ID header value to query the logs database. Once we've done that, we get back the results, which are just a list of all requests and responses belonging to that same workflow. So that's how Apex provides a solution to the first challenge of diagnosing network faults. So onto the second challenge, managing fault handling logic without relying on client libraries. So like a service mesh, Apex also has a config server, the Apex config store component, which stores all config data in one place. So in this way, Apex's architecture can be thought of as a sort of service mesh light kind of architecture. That configuration store contains service credentials for authenticating every service, right? So that's the first block in the diagram at the top, service credentials. And that's just authentication for Apex. So that's not a sort of authentication as a service kind of product. This is just so that service, Apex knows that when it gets a request, it can verify that that comes from the service it knows about, not just some random sort of client on the public internet. The second block of config data in that diagram is the service hosts information. So that's just a list of all the host names for every service, so that Apex knows where every service lives for routing purposes. So the remainder of the config data currently pertains to retry logic. So that first block, default block, defines the retry logic for the global defaults retry logic for every pair of services. So we've got timeout, 3.5 seconds, and then maximum number of retry attempts at 4, and also a back off of 5 seconds between every request, every retry. But the remaining 2 blocks, orders shipping and shipping inventory, defined what we call service-specific overrides. So these are, if you, let's say for orders shipping, let's say you want the orders service to have a different set of retry logic whenever it calls shipping compared to the global defaults. So you want some overrides. So this is where you could define them. Right? You specify the pair of services that you're trying to, that need a different set of retry logic, and you just simply define that logic in the config store. And so how that config store is used is whenever Apex gets a request, it queries the configuration store multiple times. Right? First to authenticate that request, and then secondly to route the request, so to get the destination host name, and finally to retrieve the retry logic for that pair of services. So in this case, in the diagram, for orders shipping. So that's how Apex is able to have just one place to manage fault handling logic. And again, the admin UI provides a convenient way to manage that logic, so you can view and update that logic on the dashboard. So at this point, I want to quickly revisit the comparison between Apex and the service mesh. So they really occupy opposite ends of a spectrum. Apex aims to be easy to deploy and operate, but it is a potential single point of failure. So it does trade off on some availability and scalability. Whereas service meshes are highly available and scalable because they make use of so many sidecar proxies working together, and there's no single point of failure. However, for some deployment patterns, it is also more complex to manage. But despite being on opposite ends of that spectrum, Apex is actually recognized by several major vendors of API gateway and service mesh solutions as a transitional architecture in adopting a full service mesh. Right? So that means that for teams that aren't quite ready to adopt a full service mesh yet, they're not quite giving up that option by adopting an architecture like Apex's. In fact, the opposite is true. Adding a solution like Apex to their architecture can make it easier to migrate to a service mesh later on. So Kong calls this architecture an internal API gateway, as we've already mentioned, a term that we've already mentioned a couple of times in this presentation. Citrix calls it a service mesh light, and Nginx calls it a router mesh. I want to dig into the router mesh a little bit more, just a tiny bit more. So this is what Nginx says about the router mesh model. It's relatively easy to implement, powerful, efficient, and fast. And in their diagram for the router mesh model, you can see that they have an Nginx plus proxy in the middle of their services, very much like how Apex is deployed as well as another Nginx plus proxy instance that acts as a front proxy. And in fact, in their opinion, this architecture is sufficient for many smaller systems. And so finally, I wanted to quickly describe some of the technologies we use to implement Apex. This is the same architecture again, but now we are showing our choice of technology for each component. For the proxy itself, we chose Node, just because it's known to be able to handle a large number of simultaneous connections with high throughput. And we also chose the Express framework because of it's quite fast, and also its middleware pattern makes it easily extensible. To store the logs, we chose a time series database, timescale DB, seeing as logs can be thought of as a type of time series data. They're append only, usually arrives at the database in time order, and also time is a primary axis when you query often. And timescale DB in particular has very fast ingest rates, 100,000 plus rows per second, even when the table reaches billions of rows. And this is important because, as you might remember, for every request response cycle, we log at least 4 logs, right? We send at least 4 logs to the database: the initial request, the proxy request, the initial response, and the proxy response. And for the configuration data, we chose Redis for its high read rate. And again, this is important because for every request response cycle, we read from Redis a few times, 3 times at most. And together, those the combination of those 3 fast components helps us minimize latency. As you might remember, Apex is potentially a bottleneck in the architecture, and so we needed to make sure that we do as much as possible to minimize the additional latency. And in our initial load tests, we found that Apex adds just less than 1 second of latency to every request response cycle, which we thought was acceptable for some workloads. And moving on to deployment, each component is Dockerized, and the deployment is coordinated with Docker Compose so that we minimize the chance of environment-specific issues in deployment. And we also decided to support deploying to AWS ECS for a more managed solution. Finally, to further minimize latency and security risks, an architecture like Apex is best deployed to the same VPC as the services it proxies. So that's it. Thank you very much for your time, and welcome any questions.
Thank you, Kelvin. If there are any questions from anybody, I guess it would be better to write them, to not cause too many issues. Unless you're very brave and you just want to talk.
Yeah, so can you actually deploy Apex on multiple servers, and that takes away the single point failure situation away? So is it possible to actually deploy containers and Apex on multiple servers or on containers, and then you can get rid of that single point failure problem?
Yeah, so I think that's certainly the I guess the next step for us would be to support the option of replicating the proxy, because that's the single point of failure, so that, and then maybe potentially load balance across them, right? So that would be the obvious solution to the single point of failure problem. So yeah, thanks for pointing that out. That's exactly right.
Yeah, thanks. Yeah.
Any more questions? Maybe I'll repeat it. Is storage a constraint for Apex? Storing logs require large disk space usually.
Yeah, that's a great question. So right now, I think the solution to that is to back up logs to a solution like S3 or S3 Glacier. So right now we don't support that yet, but that again, that's something that's a logical next step, an obvious choice for an obvious next step for us. So yeah, yeah, you've identified a constraint there, a storage constraint, and you're right. We do one thing we do is keep log bodies compressed, because often, especially if you've got HTML document, right, those can go up to a couple thousand kilobytes. And we decided to keep them compressed, but at the expense of human readability, right? Because then they're just a sort of a hex string in the database. But that does help with the latency involved in writing each log to the logs database, and also just minimizing storage space. So logging asynchronous or synchronous. So logging right now is asynchronous. Again, I think this is very much goes back to Ashutosh's question, because logging is potentially a bottleneck. In fact, that was the first bottleneck we encountered when we ran our load tests. In fact, the writing logs to the logs database caused some of our requests to fail because it was taking up so many of our connections. And so we have to make sure that it is asynchronous, and also we have to batch our logs as well, so that that the logging didn't become a bottleneck. Yeah, that was a long answer to your question. Yeah, asynchronous, 100%.
Any more questions for anybody? All right. Should we take a 5-minute break? Be back at 7:15 with Sava's talk. Thank you very much, Kelvin. Good talk.
No problem. Thank you. Thank you for giving me the opportunity.